Hello, everyone. This is Professor Burns. I'm really excited to be back with you guys. And what we're going to be going over today is we're going to go ahead and continue with our um, conversation or our instruction. We're going to continue with my instruction on caches. And we're going to go a little bit more into detail about how to get the bit layout and determine the number of bits for particular sections of a cache. So I'm going to start out with, as I'm going to go ahead and share my screen. All right. Let me start the slideshow. All right. So this is actually lecture 6B. Calling it 6B because it's kind of like the second part of uh, the lecture that I did a few days ago. But anyway, here's some of the things we're going to go over. We're going to go ahead and review what a set associative cache is. From the last lecture, keep in mind that we talked about three different types of structures you can use for a cache, right? The direct mapped, the fully associative, and then we also talked about the set associative. The set associative is probably one of the more common of the two. One, the direct map. If you remember that from the last lecture, direct map caches have one address associated with one particular location in the cache. And that is not advantageous in terms of the misses that you would get, right? Since it's kind of rigid and you just have one per memory, you get a lot more misses. Whereas when you deal with the fully associative and the set associative, you're allowed to map that to different areas of the cache. So that gives you a little bit more flexibility and in turn also decreases the amount of your misses when you're doing your search algorithm. All right, so set associative caches. We're going to talk a little bit about that too in the next slide. We're going to go over some of the cache terminology, particularly how those terms relate to and how they're relevant when we look at the bit structure and how it's set up for set associative cache. And then we're also going to do some cache bit calculations. So that'll be the remainder of this lecture. All right, so what you'll see here is kind of our, um, our set associative cache layout here. And this is a horizontal view, but we can also view it vertically, and we'll do that in the next slide. But remember that the difference between this and a fully associative is there's a few differences. One, if you'll notice, these are all sets, right? 0, 1, 2, 3 refer to each of these sets. And for this particular one, this is a four-way associative cache. So there are four, I'm sorry, it's a two-way associative cache, but there are four sets within this cache, right? So this is the number of sets is how many are you going to have in a particular cache, right? When we talk about the associativity, we're talking about the number of lines here. So this is considered a line or a block. The term block and line are used interchangeably, but this is my block, and this is where I would store the information all laid out. And you'll notice how it has two of these, right? This is a two-way cache because it has two-way associative set associative cache because it has 1, 2 per block. Same thing here, 1, 2 blocks per set, 1, 2 blocks per set, 1, 2 blocks per set, right? So that's why we call this a set associative. And this is a two-way. You'll also notice that when we do our searching algorithm, it's looking at the search sequentially, and this is how you enter in the data. You're going to go to this one, you're going to search for that one, you're going to search for that one, and so on in terms of when we do our searching algorithm. And another thing to note is, we talked about this a little bit last time, is that you can actually search all the entries in one set at the same time. That means as I'm doing this search, I'm searching everything. If I'm searching set 0, that means I'm searching everything that's in this set. Everything, both of these lines, I'm searching at once. If I'm searching in set 1, I'm searching both of these lines at a particular time, as opposed to searching it one at a time for just one memory location. All right, so now let's kind of review some of the cache terms. A set is a cache line of multiple blocks. So a set has multiple blocks in there. I don't know if I want to call it a line, but it's a cache object with multiple blocks in it. A block is a cache storage unit. So that's like one unit within your cache, right? And your tag is really your memory location. All right, so we can also talk about some of the things we use for our mapping and some of the variables we use for mapping. We can say if you consider S as the number of cache, the cache set, excuse me, N can be like the number of blocks or lines in a set, or N is also known as the associativity. It's an N-way cache. That means it's a, these are the number of blocks within a set, so it's an N-way associative cache. That tells you the number of blocks or lines within a set. So some people, when they do their examples, they might say this is an N-way cache. If it's a two-way cache, it's 2 blocks within a set. If it's a 3-way, it's 3 blocks within a set, but you're not typically going to have that. It's usually like 2, 4, 8, etc. But whatever the case may be, it's an N-way, meaning it's going to tell you the number of the number of blocks or lines within a set. A word, the word is the data item that will be stored. All right, your word is your data item that will be stored, and typically one word is equivalent to like 8 bits of information, so you want to keep that in mind as you do some of your calculations. And as we go a little bit more into these mapping variables, you want to understand what your offset is. The offset refers to the number of bits that are used to store the cache blocks or lines, and V is the validation bits, right? So we're talking about all these things because they will help us as we go on and we determine kind of what we're looking at in terms of these the bits in their variables. Now, the validation bit, it was said in one of the tools that I posted. It's just a way to determine whether or not the information that you're accessing from the cache, is it valid? Is it data that you need to be accessing, or is it something else that you don't really want to pull from memory? So let's look at a layout. Like, what if we said n is 2? So n is 2 means that, right, I have a 2-way cache. That means there are 2 blocks per set. And if I were to tell you that there's a total number of 8 blocks, I can use this information basically to give a layout of my cache. How do I do that? All I need to know is the number of the associativity of the cache, and then I need to know the number of blocks, and I also need to know the number of sets. Now I have the information here where I can calculate the number of sets. So then I can say, okay, I have my association, I have my number of blocks. All right, based on that, I can go ahead and determine my sets. If I know I have 8 blocks and I know that my associativity is N or 2, I know that I have a total of 4 sets. 4 sets will allow me to block everything or to map everything with my blocks. So this is my total number of blocks. That means if I have 4 sets, I can go ahead and map everything I need for that particular memory for that example. And this is kind of what it looks like, right? If this right here is my cache example, what you'll see right here, if I'm looking at this one item here, right? This is kind of my one line, right? This is my set here, set 0, set 1, set 2, set 3. Now I did it vertically this time just to make it a little bit easier to see, but you'll see that if I look at it here, here's my layout. I have this first bit can be considered kind of validation bit. Then I have some sort of tag, which is going to be my memory information. And then the word is going to be what data that you're looking at. So that's one way to look at it. But if you'll see, I've already calculated what I need to represent this, right? Really, I have these kind of 8 blocks, right? Here's my first block. Let's go ahead and draw this. This is my first block. Right here. This is block 1. This is block 2. And that's set 0, right? So we have 1, 2. Then I go down here. This can be 3, 4. And these numbers in red again are my blocks. 5, 6, this is my block, 7, 8, and look at that. I have told you how many, I have 4 sets, right? 0, 1, 2, and 3. These are my 4 sets. I have my 8 blocks, right? With 2 blocks per line. And this already has given me what I need as my structure and my layout for my cache, right? Because I had what I was starting out with, total number of blocks. And based on that, I was able to map out and give kind of an orientation for how I want that to look, right? This is how I would set it up. And this is just a very, very simple example. Real caches are not going to be the simple, but just to give an overview of how we map this out. If I know my total number of blocks, if I know my associativity, I can then map out how I want my cache to look. All right, so let's go ahead and clear all that. And now we're going to look at a little bit more of a complex example. And we're going to talk about how we well, we're going to talk about a little bit of what this means, right? This is kind of one way that we can represent our bits, but it's actually a little bit more involved in this, right? We have the validation bit, we're going to have the tag bit, we're going to have the word, but another way to represent this would be looking at it in this perspective. And this is a common way to look at it when you're looking at your tag, your hash bit layout. Now it doesn't vary too much from this, right? You're always going to have your tag bit. The tag may not always, or the validation bit may not always be shown in this particular one, but it's sometimes just added on to it. But you have your tag and then your word is all the other information. So when we look at it here, the common calculations that we do for the cache for a set associative would be what you need for your tag, what you need for your index, and what you need for the offset. Now all of that, the index and the offset, these things are associated with how we are organizing this in the cache, right? So keep in mind, we're pulling information from the main memory, and I have now this new structure that I need to be able to tell people how to navigate that. So this is a method that just tells you how to navigate the cache so that I can get into the memory information that's actually located there, right? So let's go ahead and get to it. Total memory. This is super simple. That means if I add up all of these, this will tell me the total number of bits I need to represent for my entire memory, right? If I have 1 gig of memory, then that means that this should add up to something, the number of bits should add up to what I'm going to need to represent to a 1 gig memory, right? 1 gig of memory is 2 to the power of 30, right? So I will need 30 bits kind of all added up to represent those items in memory. The offset, all right, so this right here, the offset number of bits, and these again is the number of bits that we're using to represent these. Offset bits, how many I'm gonna need, that's gonna be that's gonna index my blocks or lines, right? Blocks or your word or your data, that information that's going to be included within the set. So your offset tells me how many bits you need to represent your number of blocks, right? And however many blocks you have, you're going to have 2 to the power of that to where that the power that it is going to tell you what the number of bits you need for the offset. Index. The index item here is just including the bits needed for my cache sets. So the total number of cache sets, that's going to be whatever, that's going to be the number of bits that I need to represent my cache sets, right? And remember, the sets are going to be those row items. The lines are going to be each of the things in between. And then what's left over is going to be my tag, which is the actual memory location. All right, so hopefully that makes sense. Your tag, we've already went over that. That's your actual memory location. But when you're looking at the cache layout structure, you have all these additional bits that are included so that you can organize your thoughts or organize how you want to search through the actual cache. So, excuse me. Let's go ahead and look at an example. All right. So let's say we have a set associative cache with 8 sets, and each block is 16 bits in size. it's an 8-way, the cache is an 8-way cache, and the addresses are 32 bits. Now we need to determine what bits are needed for the tag, the index, and the offset. All right, so that's going to be a common thing that we remember, right? These are, if you're determining what bits are needed, these are the typical number of bits that you're going to be looking at for this set associative cache. Your tag, index, and offset bits. All right, so we're given some information already, right? So now we want to figure out how we can get this in this structure, all right? So what we're actually going to do is we're going to start from the right, and walk backwards to the left. So we're going to start from the right because that's sometimes the easiest one to calculate. Now, what did I say the offset bits were? So I said that the offset bits were associated with, and I'll put this just in as notes, my block. That's my offset. Your index is associated with your sets. And your tag is associated with your memory. All right, so set, so memory for your tag, set, how many do you need to represent the number of sets? And then how many do you need to represent the number of blocks? Those are the 3 items, right? So from this, if I want to learn and determine what my offset bits are, do I have anything that tells me what the number of blocks are? Let's see. It says 8 sets. Each block is 16 bytes in size. So if each block is 16 bytes in size, right? That means what I'm going to have is, I now know this right here, this item right here is going to give me my first, the first set of information that I need for, for calculating this particular element, this 16 bytes right here. All right. So here's how I calculate that. For my log, for my offset, all I'm gonna do is I'm gonna take the log to the power of 2 of my block size. I already know that my block size is 16 or 16 bytes. So what happens is my the size for this is 4. All right, now you want to also keep in mind that when we're doing this, when we represent the offset, you're going to represent that in the number of bytes needed to represent your block. So how many bytes do I need to represent my particular block, right? So these are 16 bytes in size. So if I take log to the power of that, that will tell me that I need 4 bytes of information to represent the offset for this block. All right, so now that I have that, the next thing I want to determine would be my set, right? So since we're going from right to left, let's go ahead and look at the set. For the set index, we talked about what we need for that when we're looking at the set is we really need to know the total number of sets that we have in this, right? So there's a few different things that are going to be important here, right? And one of them is right here. We actually don't need the number associativity for this particular example because this already tells us that we have 8 sets. So we're going to go ahead and use that. Since I know I have 8 sets, what I'm going to do is I'm going to take the log 2 of that, and that will tell me how many bits I need to represent that. I have 8 sets. All right, so your blocks are going to be represented in bytes. Your index are going to be represented bytes per block, right? Your index are going to be represented in sets. So the number of sets, the number of bits I need to represent my set are going to be 3 because I have a total of 8 sets. All right, I have a total of 16 bytes for my blocks, right? That's the measurement for our blocks, or the unit for our blocks, bytes. Sets are going to be the units for our index. And now we have this. We have an offset, we have our index. Now we have left is the tag. Now keep in mind that I said your tag is basically gonna be what's left over from the total number of bits needed for the memory location after you get your organizational things from the cache, right? So this is organizing the cache, the index and the offset. So the first thing I need to do determine my tag bytes is figure out how many bits are needed for my memory. It already tells you that that the addresses are 32 bits long. So now I know the total number of bits I need for my memory. And from that, I can easily calculate what my tag is going to be. It's going to be 32 minus 4 minus 3. And that gives us what our tag bits are, right? So that gives us the number of bits that we're going to need to represent the address of the memory, right? So here's what that looks like. After our calculations, we got 25, 3, and 4, with 3 being our index bit, 4 being our offset bit, and 25 being, I'm sorry, our number of offset bits, excuse me, our number of set bits and our number of tag bits are 4, 3, and 25 respectively. All right, so let's look at one more example like that. All right. Now let's say we have, this is the same example. This is actually the exact same example. Well, let's do a little bit of a different example. So this is one we're looking at eight something that has 8 sets. It's gonna have 16 bytes in size and then 32 bits, right? But if we wanted to change this up a bit, we can also look at a different example. So let's go ahead and continue. Let's say I had something like this. Let me go ahead and clear the whole drawing. Let's say I have an example like this, right? It's a little bit different than what we were looking at before. But let's say I have a main memory size of 256 megabytes, right? 256 megabytes means my main memory is the size of, that tells me my main memory size. It also gives, if I have a cache that's 1 megabyte and I have my blocks and I tell you that it's two-way set associative, how do I go ahead and then calculate or determine these 3 items right here? Well, we'll do the same method in that we're actually going to start from the left here and go all the way to the right. I already know it tells me that I have 128 bytes, so I can calculate the number of bits I'm going to need to represent that by taking the log 2 with the log base 2 of that to give me 7. So now I know my offset bits is equal to 7. Now, when I get to the index, right, keep in mind that my index refers to really the number of bits needed for to represent my sets. This example does not give you the number of sets. So we got to do a little bit of calculations here, right? I don't know how many sets are here, but I know a couple things. I know my cache size. So I have the total size of the cache. I also know my number of blocks. And I know that it's two-way set associative, right? So based on that information, I could go ahead and determine how many sets I'm going to need. I have the information right there to tell me. So the first thing I'm going to do is let me figure out how many lines are here. Now, let's take a little bit of a step back, right? If I want to determine my cache size, I have 1 megabyte, right? We know that 1 megabyte is 2 to the power of kilo is 10. Mega is going to be 20. So my cache size then, those bits are going to be 2 to the power of 20, right? That's my total size. And then I also know, I need to know how many lines I'm going to have. So what I can kind of do is I can divide the total cache size by the number of bytes, right? Because my blocks, that will tell me how many blocks I have in there. Then once I determine how many blocks I have, I can divide that by the number of blocks per set to give me what I'll need for my number of sets. So my cache size, remember I was saying that is 1 megabyte or 2 to the power of 20. It's going to be here. My block size, as we said before, is 2 to the power of 7. So that means, just based on that my number of lines, what I'm going to need to represent that, is going to be 13 bits. But wait, there's more. So now I know how many lines I have, but keep in mind there's some associativity with this. That means I'm not going to need the same number of bits for every line because I have a two-way cache. So for the number of sets, because I have a two-way cache, that means I can have 2 items per that. So I can go ahead and get my number of bits for the set by just dividing that by 2. Or another way to say that is you're going to divide that by 2 to the power of 1, meaning that now I only need 12 bits to represent my number of sets, right? So based on what the information we had here, we were able to determine what we needed, the number of bits we needed for the set. And this goes all into our index. Our index then is going to be 12. All right, so now we have our offset. We have our index. The last thing is the tag. Tag is relatively easy, right? All we do is we take the main memory size and we subtract these other two numbers that we already have. So main memory, 2 to the power of 56, which I think is 2 to the power 256 megabytes. 256 is 2 to the power of 8. A megabyte is going to be 2 to the power of 20. So that means that my bits for memory is going to be 2 to the power of 28. So now I have my bits needed for the memory, and I can easily go ahead and determine what's going to be the tag bits from that. So I say I'm going to take the total, subtract the offset, subtract the index, and that gives me 9, which is what I'll need for my tag. So here are the final numbers and the final values for that, right? So here's my all the bits, and it's kind of this layout for this set associative example. All right, we're going to go ahead and continue with the rest of this. We're going to look at another example for calculating or determining the bit structure layout for cache. So in this example, we have 128 M or M words. We have 64 blocks. I'm sorry, each of the blocks are 64 words in length, and the cache consists of 32K blocks. If we assume that it's a two-way set associative cache, it wants us to go ahead and show the mapping scheme. And again, just as a reminder, what we're looking for, this is going to be our tag. This is going to be our index. And this is going to be the offset. All right, so let's go ahead and get started with this. We're going to, as we did before, go ahead and start from left, from right to left. I'm going to actually delete this and try to write this a little bit more organized. This is our index. All right. So now that we have this here, let's start off with the offset, which I'm going to call O. That's just going to be equal to our log 2 of the total number of bytes. All right, the blocks we need for the bytes we need for our blocks. Now, what I do want to make a note of here is it gives us, it says the blocks are 64 words long, right? Um, if you guys remember when I talked about the unit of measurement for the offset, or the unit of measurement that we're using for our lines or blocks are going to be in bytes, right? One word is the same thing as 1 byte, which is the same thing as 8 bits. So that's all the same. One word is 1 byte. That's the same thing as 8 bits. So since our unit of measurement is already for this, we're using bytes. When it says these are 64 words long, that's the same thing as saying it's 64 bytes long. All right, so I'm gonna go ahead and say that I already have this. So it's just gonna be the log 2 of 64, which is gonna be equivalent to log 2 of 64 should be 6. And now we have our offset here, all right? So again, all we did was we took this value here, um, where they told us we were given the length of the bytes. I actually don't like that. We were given the length of the bytes, and we use that to determine what to use for our offset. So that is relatively simple. We have what we need there. Now we're going to go on and let's look at our index. Now for our index, keep in mind that that is associated with your sets. So in order to get our number of bits for the index, we first need to determine how many sets are in this particular example. Now when we look at and we consider the number of sets, we want to look at, they don't tell us exactly the number of sets, but we are given that the cache is 32 blocks long, right? So C equal 32K. All right. And I'm given now K blocks. This is an important part right here. That is 32 K blocks, right? It is not bytes, but it's blocks. So this is the same thing as saying 32 lines, right? 32K line. So now I have the number of lines, right? Which makes it a little bit easier than the example that we had before, because this is telling me this is the number of lines that I have. So I'm like, okay, I have this. Now that I know that, all I need to do is if I take this and I divide this by our associativity, that means I have a total of 32K blocks, 32K lines. I can determine the number of sets I have by dividing that by my associativity, right? Because if I were to say I have 32, 1,000 lines, but my associativity is 4, that means I have 4 blocks per line. So that's why I go ahead and divide this to figure out how many sets I need. And the number of sets I need are 2. Now, keep in mind that we are trying to get this in terms of bits. So we're going to have to do a little bit of conversion here to get our, to kind of get this in the power of 2. So I'm going to break this down in 2 aspects. Let's look at 32 itself, right? 32 is going to be 2 to the power of 5. And then that's going to be multiplied by 2 to the power of, when we're looking at K, you can consider that 2 to the power of 10. Right? And then since we're multiplying these together, it's going to end up being 2. Oh, I'm sorry. I see something right there. Let me go ahead and adjust that. I said that I'm not multiplying this, but I'm actually dividing it. So let's get that out of here. And let's just clean that up a little bit. Keep in mind, we're dividing this because I don't want to multiply it. I want to say this is going to be, I'm going to need less sets since I'm putting 2 in it per row. So 2 to the power of Oh, I'm sorry. That was right. This is just determining k right here, 2 to the power of, so that was right, 10. And that's all going to be divided by this is all going to be divided by 2. All right, or 2 to the power of 1. So now I have 2 to the power of 5 and 10. That's going to give me 15 divided by 2 to the power of 1 is going to give me 2 to the power of 14. So again, the way we did that was we said, this is my top level. This is my number of blocks, the total number of lines, 32K. So it's going to be 32 times our multiplier here, 2 to the power of 10. That gives me my 2 to the power of 15 for the total number of lines. Because this is a set associative, I also have to consider what the information is when I have my certain number of lines per set, and that is 2 or 2 to the power of 1. Once I combine that together, I get 14, and that gives me my index. Okay, so now we have our offset, and we also have our index. All right, now the only thing that remains is our tag. And as we stated before, your tag is relatively easy to get once you have determined the full size in memory, because all you do is you take your memory and you subtract the bits you had for the offset and the bits you had for the index. So this gives us our memory somewhere up here. It says that the memory is 228 M words. Now our memory is going to go ahead and stay in terms of the bytes and everything that we need for that as well. So when we calculate what we need for memory, we can go ahead and say that this is going to be total number of bits we need for this is going to be 2 to the power of 128. All right, if 64 is 6, 128 is 2 to the power of 7 times 2 to the power of meg. Again, it's going to be 10 times 10. That's going to be 20. All right, so the number of bytes that I need for my memory, right? That total number is just going to be 2 to the power of 27, which means I would need 27 bits to represent those words. And this gives me the amount of bits that I need to represent each word in memory. So what that basically means is now I have my total. I'm going to go ahead and use that to get my tag. My tag is going to be, we'll call that T, is just going to be equal to memory minus offset minus my index, all right? So that's going to be 27 minus 14 minus, let me clean that up a little bit. I'm gonna do minus 6. Let's clean this up a little bit. Just so it looks cleaner. So it's 27 minus 14 minus 6 should give us what we need in terms of our tag. All right, so given that, this gives us 7. And now we have all of our information for this particular bit. So again, if we're looking at this in review, your offset bits, we use the total number of words in the blocks to calculate that, right? Log 2 of 64. For index, the first thing we had to determine was the number of sets that were available. Given that we were given the number of lines, right? The number of blocks is equivalent to the number of lines. We have 32K lines. We can use that. We divide that by the associativity, and then now we know the number of bits that are needed to index our sets. And then finally, last but not least, we take all of that, uh, we subtract these two items from our memory to get the number of bits that are attributed to the memory address or to the tag portion of our associativity of our mapping. And that's basically the summary of how we would go ahead and make those calculations. So you guys want to definitely keep all this in mind as you run this information. Keep all that in mind while we're doing this so that you have a basic idea of how you want to run it, and it makes it easier to do those examples. The important part is just to look at what they're giving you, what the question is giving you, and then break it down like this. The more and more you break this down, then easier and easier it will get. And that's pretty much it for this lecture. Thank you guys so much for joining. Um, this will be a part of the quiz that you're gonna take. And that's about it. So until next time, enjoy the rest of your day.